This podcast is called Matrices Solving Systems Using X equals A inverse B. I immediately make reference to a matrix called A inverse, and I need to make a couple of points here. First point is that only a square matrix has an inverse. Only square matrices have inverses. And what that's going to do is that's going to limit the types of solutions that we can make using this method. This method will only be usable when A, the matrix of coefficients, is a square matrix. And what that means for us as far as our problems is, this is useful when the number of variables equals the number of equations. So if we have a system of 3 equations and we have 3 variables, this is a useful method. But if we have 3 equations with 5 variables, this method will not solve the system. Now, what do I mean by an inverse matrix? Well, I say that B is the inverse of matrix A, written B equals A inverse. That symbol means that A times B is equal to B times A is equal to I, which means the identity matrix. So here in this first example, I've got a two by 2 matrices. Matrix A is 3, 5, 1, 2. Matrix B is 2, negative 5, negative 1, 3. Now I'm not going to take the time to load them in the calculator and multiply them. You can do that. It's very fast. It's very easy. But when you multiply them together, you get the matrix 1, 0, 0, 1, which is the 2 by 2 identity matrix. So I've multiplied A, B together. I've got the identity matrix. That means that A is the inverse of B or B is the inverse of A. Now we're not actually going to be doing this step. We're going to go straight to the formula X equals A inverse B. But we won't be loading A inverse in our calculator. We'll be loading A in our calculator and using the inverse key to get A inverse, but we'll never really see A inverse. We'll just see the solution. Okay, here's how you use the formula. It says if a system of n equations with n variables, again I want to emphasize, this is only going to work when the number of equations and the number of variables are equal. So if you're thinking about using X equals A inverse B, count your equations. If you've got 3 of them, count your variables. If there's 3 of those, then you can use it. If a system of n equations with n variables can be written in the matrix form AX equals B, and if A inverse exists, and it won't always exist, just because A is square doesn't mean it has an inverse. But if it's not square, it doesn't have an inverse. If it is square, it may or may not. If it does, then the solution of your system is given by X. The variable matrix is equal to A inverse B. Okay, let's jump right into some examples to see how they work. The first example says solve the system 3.2x minus 4.6y equals 2.1 and 2.3x plus 1.5y equals negative 16.1. Now, we have in an earlier section learned how to solve a 2 by 2 system by graphing. And what we do is we solve each equation for y. We load it into our graphing calculator. We graph it, and wherever the 2 lines cross, that's our solution to the system. So what I've done over here on the left is I've solved the first equation for y. I moved the 3.2x over to the right so that it would become negative 3.2x plus 2.1 on the right. Then I divided both sides by negative 4.6. This was my result. I did the same thing for the second equation. Now if that's a little quick for you, just pause your podcast and stop and do that for yourself and see that those are the solutions. And now let's bring up the calculator. So here's my calculator, and I'll show you that I've already entered the 2 equations in. Here we can verify it. Negative 3.2x plus 2.1 divided by negative sign 4.6, and I also have the other one in there correctly. And let's do a quick zoom 6 for a graph. And there's the first line graphing. And there's the second line graphing. Now if we want to solve this system, we can trace over to where they cross. where's my tracer here? There we go. We're tracing over to where they cross. There we go. That's pretty close. And then once you get pretty close, you can do your second trace 5. Second trace 5 is intersect 5. Enter, enter, enter. And we get that the intersection point is negative 4.61. So x is negative 4.61. Y kind of got out of my eyesight there. And y is negative 3.66. Each time I mark on the screen here, the calculator goes down to the bottom, so I can't get to it. Okay, let's see what we do now if we use the x equals a inverse b. In the system, the rule says if we can write the system in the form ax equals b. So here I've got a, the matrix, times x, which is the variables x and y, is equal to b. Now a is the matrix of coefficients. Coefficients are numbers that multiply the variable. So the first thing in a would be 3.2 because that's multiplying the x. A is, what goes here is not 3.2x, it's just the 3.2. The coefficient of y is negative 4.6. The coefficient of x in the second equation is 2.3, and the coefficient of y is 1.5. So now I've got a times x. B is the matrix of constants. The constants are 2.1 and negative 6.1. So I put 2.1, negative 6.1. Now we're going to have to load A and B into the calculator. So we'll do that. I'll bring up the calculator. I'll go ahead and clear this off. We're not using this anymore. And if we're going to load the A matrix into matrix A of the calculator, we go matrix, edit, and for matrix A that's a 1, so down here I hit a 1. That brings up matrix A. Now you can see that matrix A right now is a 1 by 1 matrix. We wanted A to be a 2 by 2 matrix, so I put in 2 enter, 2 enter, and immediately this changes to 2 by 2. The numbers enter by row. So the first row is 3.2, negative 4.6. So I go 3.2, enter, negative 4.6, enter. And I've got the first row in there. Second row is 2.3, 1.5, 2.3, enter, 1.5, enter. And I have loaded matrix A. To load matrix B, I'll go matrix, edit, 1, 2, B is number 2, and I'm editing B. And I want B to be 2 by 1. It's got 2 rows, 1 column, so I'm going to go 2, enter, 1, enter. And now it's 2 by 1, and again enters by row, so 2.1 for the first row, enter, negative, that says negative 6.1 here. It should say negative 16.1. Let me see if I can erase that. Negative 16.1. Didn't really give myself enough room in that matrix to write. So negative 16.1, enter. Whoops, error syntax. Let's see what happened. Oh, I didn't use a negative sign, I used a minus sign. So let me change that to a negative 16.1. Fumble fingers. Negative 16.1, enter. And now I've got in matrix B. Now the solution is A inverse B. So I'll just quit out of this. I go second quit. Now I'm back to my home screen. And I can't just print an A here. I need a matrix A. If I just go alpha A, I'm just going to print an A. The A I print needs to look like a matrix, so I'm going to go matrix 1. And that prints out the matrix. the letter A with the matrix bracket around it. For inverse, I go here to my X inverse key. So there's matrix A inverse. Now if I want to, I can put a times sign. If I don't want to, I don't have to put a times sign. If no sign is here, it will assume a times sign is here. So I'm just going to go matrix 2. And matrix 2 is matrix B. And A inverse B is supposed to be my X, my variables. So I hit enter. And I get, lo and behold, negative 4.61 and negative 3.66. And notice that those answers are the exact same answers we got when we did it by graphing the two lines and seeing where they crossed. And I think you'll agree that this is probably an easier method than graphing. Here you just do your matrix of coefficients, enter it, your matrix of constants, enter it, and type in A inverse B, matrix A inverse matrix B, enter, and you've got your solution. Let's go on to another example. The systems you're given, you're not always given in a nice, neat form like this. This was so easy to set up. It was easy to see what the A matrix was, easy to see what the B matrix was. That's not always the situation. Suppose I gave you the following problem. It says solve for A, B, and C. And if I just said solve, it would automatically be for A, B, and C. Now, when you look at this, I'm saying that I've got a matrix on the left and a matrix on the right, and I'm saying the two matrices are equal, and I'm saying they're both 3 by 1. When you look at the matrix on the left, you might be tempted to think of that as being 3 by 2, because it looks like there are 3 rows, and it kind of looks like there are 3 columns. But here's what it would look like if it was really 3 by 2. The first elements would be clearly distinguished away from the second elements, and this would be 3 by 2s, 3 rows, 1 column here, 2A, 2B, and A, and a second column here. That's not what I have in this problem. This is a 3 by 1 matrix. Just as A is a number, 3 times A is a number, and 3A minus B is a number. This whole expression, 3A minus B, that's just one number, and this is just a 1 column matrix. And it has to be in order to equal the second matrix, which is clearly a 1 column matrix. Now, I could have given you this problem in a different format. Recall that we said for two matrices to be equal, they have to be the same size. Well, both of those are 3 by 1s. And they have to be equal position by position. Well, if they're equal position by position, that tells you 3A minus B equals 4. It tells you that 2B plus C equals 1. In other words, this is the second row, first column. This is the second row, first column. 2B plus C has to be the same as 1. So I could have given you the system in this form instead of in the form that I gave it to you. Both of those are the same. But how do I get that into the form AX equals B, where A is a matrix of coefficient, X is the matrix of variables, and B is the matrix of constants? Well, in our previous example, all my variables were on the left and only the constants were on the right. Notice that in this system, I've got a constant on the right. So these are going to have to be modified a little bit. I could rewrite the first equation as 3A minus B plus 0C equals 4. The second one as 0A plus 2B plus C is equal to 1. And then the last one, I could move the C over to the left and the 7 over to the right. And then it would say A plus 0B minus 2C is equal to 7. And now that I've got the thing in the right form, I can go ahead and fill in my A and my X and my B. My X, of course, is my variables. So that's going to be A, B, and C. And notice there's 3 of them and exactly 3 equations. So this is a good problem for using this method on. Now I need my coefficients. In the first equation, that would be 3, -1, 0. In the second equation, 0, 2, and 1. And in the third equation, 1, 0, and -2. For my constants, after I move the 7 over, my constants would be 4, 1, and 7. So I would have to enter for my A matrix this 3 by 3, and for my constant matrix, my B matrix, this 3 by 1. Well, I've already done that to save time. At least I've entered the 3 by 3 into matrix C. Let me show you that. If I go matrix, well, turned off. If I go matrix, edit, C, which is number 3, it shows it to be a 3 by 3, 3, -1, 0, which is what I've got for my first row, 0, 2, 1 for my second row, 1, 0, -2 for my third. I actually did not load the B matrix, so I'm going to go back and reload the B matrix in matrix B of the calculator, that is matrix 2. So I'm going to say to load matrix B, I'm going to go matrix, edit, 2. Right now it's a 2 by 1. I need it to be a 3 by 1, so I go 3, enter, 1, enter. And I enter my numbers 4, 1, and 7. 4, enter, 1, enter, 7, enter. So now I've got my matrix B. But remember, I've stored matrix A into location C in the calculator. So instead of writing AX equals B, like I normally do, this time I'm going to write CX equals B and use X equals C inverse B instead of A inverse B. So I quit out of this. I want to write, well, let me clear this off. We don't need this anymore. I want to write X is equal to C inverse B. So I go matrix 3, that's C. To get C inverse, I use my inverse key. For matrix B, I want matrix 2. C inverse B, enter. And there are my answers. Positive 1.92 for X, 1.77 for Y, kind of a poor 7 there, and for Z, negative 2.54 right up here. See the 3 answers. Z is negative 2.54. That's a very appropriate way. That's called an ordered triple. In an ordered triple, the first number is your X, the second number is your Y, the third number is your Z, and we have solved a 3 by 3 system. Remember the point of this system? I could have given you the problem this way. I could have given you the problem this way. Both of these are the same. Make sure you understand that very important point, and make sure you understand that both of these need to be changed to this form before you can properly pick off your coefficient matrix and your constant matrix. Well, let's go on to our last example. Our last example, first off, it's very confusing looking. There's letters on both sides, numbers on both sides. Different equations have different variables. The first equation has 4 variables, W, X, Y, and Z. Second equation, W, X, and Z, X, Y, and Z, W, Z, X, and Y. There are 4 variables, W, X, Y, and Z. And notice there are 4 equations, so this is a good system for trying our X equals A inverse B on. Equation 1 is not too bad. I could get it into the proper form by simply bringing the x, y, and z over to the left. So for equation 1, I'm going to write 2w minus 3x plus 4y plus z equals 0. When I bring my x, my y, and my z to the other side, that leaves no number on this side, so equals 0. The second equation is not as easy. I've got these two variable terms in a bracket multiplied by a number. So before I can get anywhere with this one, I'm going to have to distribute that out. I do that down here. Here's my new equation 2. I write 3x, then I distribute the negative 2, minus 2w minus 4z equals 16. Now, in my first equation, I put the w first. So as I'm rewriting this, I have to put the negative 2w first, the x second. There is no y. I'll put a plus 0y. And then minus 4z. And this time we do have a constant that is equal to 16. And we're on to the third equation. The third equation is set up right. My x, y, and z are on the left side. My x, y, and z are in the proper order, so I don't have to switch anything around. The one thing that is a little bit wrong here is I'm missing the w. So it's going to be 0w. You don't have to write that. You could just write plus x minus y minus z equals 4 and leave the 0w off if you want to. Doesn't matter. And now for my fourth equation, again, I've got some multipliers, so I'm going to first distribute. On the left, I get 3w plus 3z. On the right, I get 2x minus 2y. I now need to get my w, my x, my y, and my z all on the same side. So the x is going to have to come over here. The y is going to have to come over here. When the 2x comes over here, it'll be negative 2x. So I'll write 3w minus 2x. When the negative 2y comes over, it'll be plus 2y. And the 3z stays where it is, plus 3z is equal to, well, there weren't any numbers again, so again, that's 0. So now I want to write it in the form ax equals b. But again, to save time, I went ahead and put that coefficient matrix A, I actually put it in location D. But to pull off the coefficients, you get 2, negative 3, 4, 1, negative 2, 3, 0, negative 4. Third equation, 0, 1, negative 1, negative 1. And last equation, 3, negative 2, 2, 3. And you can see here that there's no limits to the size. You can have as many equations and as many variables as you want, as long as the number of variables and the number of equations are equal. This must come out n by n, in this case 4 by 4. And remember that I already stored that in location D, so it's actually going to say dx equals, and I think I put my variables into matrix E. We'll check that. If it says dx equals E, then we'll simply say x equals d inverse E. So let's check and see if I actually got those loaded in correctly. It's been a while since I did this. We'll go to matrix, edit, D, which is 4. See if we, yeah, it looks like that's in. It's a 4 by 4 matrix. 2, negative 3, 4. To check that the last one's a 1, you have to arrow over. Oh, let's see. Got to arrow over. Yeah, it is a 1. Below that is a negative 4. Below that is negative 1. And below that is a 3. So that would correspond to this matrix here. So go back to check our first 3 coefficients. Negative 2, 3, 0. Negative 2, 3, 0. 0, 1, negative 1, 0, 1, negative 1, 3, negative 2, 2, 3, negative 2, 2. Okay, looks like that one was loaded in correctly. Let's see if I put the constant matrix into E. I'll go matrix, edit, E is 5. Yes, I put in the 4 by 1. Let me put in the X matrix here. Our variables are W, X, Y, Z, and our constants are 0, 16, 4, 0. I didn't actually put that in A. I actually put that into D, so my equation says dx, and I put this matrix of constants into E, so that says dx equals E, and x equals d inverse E. So that's all I have to do. Let's do that multiplication. I'll quit out of this. I'll clear this old stuff off. I want to do x equals d inverse E, so matrix D, that's 4, inverse is x inverse, matrix, E is 5. So there's D inverse E, enter, and there are my answers, 3.13, 5.57, so let's see, 3.13, 5.17, and we need 2 more answers. Last 2 answers are 2.96 when I round, and negative 1.39. 2.96 and negative 1.39. That's W, X, Y, and Z. And that completes the podcast on solving systems using X equals A inverse B.